Hi, this is Daniel Cunningham,
Illini Goss.
and this is our presentation on the traveling salesman problem. So we will be going over the history of the traveling salesman problem, getting all the way back to when it was first started, going over the problem itself, and we'll be going over the important applications of TSP, which stands for the traveling salesman problem, in the real world. We'll also be talking about approximations of the algorithm using meta-heuristics, ways to get around the fact that it is NP hard, and the ways to solve it without solving it in polynomial time. We'll also be talking about possible quantum algorithms that may be able to be applied in the future when quantum computing is widely available. And then we will be concluding and showing you our references. So the history of the traveling salesman problem. The traveling salesman problem was studied in the 18th century by a mathematician from Ireland named William R. Hamilton. You may recognize him from creating the Hamiltonian circuit, otherwise known as the Hamiltonian path or cycle. That's a cycle in which all of the nodes are visited, all of the vertices are visited, and then eventually it loops back to the beginning. Also involved was the British mathematician named Thomas P. Kirkman. However, since the 18th century, there have been several developments for TSP and different ways to solve the cases. So at first, we had to solve it using brute force, which is just going through every possible combination of edges and vertices that created a Hamiltonian path. This is incredibly inefficient. However, there have been more efficient solutions that have been found. None of them are in polynomial time, otherwise known as P. So the traveling salesman is an NP hard problem. It is NP hard because it has no quick polynomial time solution. And the complexity of calculating the best route will increase much quicker than the rate that the problem itself, that the input of the problem increases as you add more destinations to the problem. So the way that the problem works is that first you have a salesman who is visiting all of the cities in an area of a circuit. He wants to get the shortest possible path that visits all of the cities so that he can sell all of his stuff everywhere. However, this can be solved without brute force. We will be talking about the ant colony solution. However, there is also a dynamic programming solution as well. None of these are in polynomial time, of course. So none of these are viable methods to solve the problem computationally in a large setting. These can only be solved computationally if it is a relatively small input that can be reasonably solved by a computer. So some important applications within the real world. First of all, Google Maps. The salesman would typically be a car or any other form of transportation, such as maybe a plane or even a person walking, that picks a destination as a starting location within Google Maps and replaces their home's location as the end destination. Google Maps also has the ability to create multiple destinations along your route. And if it was able to solve the traveling salesman problem, then in polynomial time, then it would be able to find the best, not only the best route from one destination to the next, but from the very beginning destination to the very end destination. And the whole thing would be the best, and not just from the first to the second to the third to the fourth. It would be the whole thing would be optimally solved. However, Google is not able to do that because the problem is not solvable within time. Google's database is, of course, enormous. Even if we just looked at maybe one city, that would be far too big for any normal computer to solve using meta-heuristics. So Google Maps would very much benefit from a solution to the traveling salesman problem in polynomial time. Also, in a smaller scale, order picking problem in a warehouse. In a warehouse, an order is received with the items ordered placed throughout the warehouse. A vehicle has to go collect those items within the warehouse to ship them to the customer, which is where the resemblance of the TSP is seen. The item locations in the warehouse correspond to the nodes of the graph. The distance between two nodes is given by the time needed to move the vehicle from one location to the other. The problem of finding the shortest route for the vehicle pickup time can be solved as TSP. So this means that if we had a way to solve this in polynomial time in a warehouse, we could find the optimal route. So then packages are shipped on not only on time, but possibly early. This would take a lot of strain off of companies like Amazon that have to rely on their workers just picking up what they can as fast as they can. This would probably also take a strain off of Amazon's workers who have to navigate the warehouse as best they can. They would be able to leave that up to an algorithm that would tell them where to go, how quickly, in what order, and they could grab things and put them onto trucks to then be transported as fast as possible.
And I will be talking about the ant colony system, which is also metaheuristic. The ant colony system is one approximation algorithm which uses metaheuristics for the traveling salesman problem. The ant colony system is inspired by the observation of real ant colonies. It uses the observation of ants' pheromone trails for food to get its information for the algorithm used to solve the TSP algorithm. The ant colony system solves TSP by observing the behavior of ants as they gather their food. During an iteration of the AS algorithm, each ant builds a tour executing one step for each node or city. For each ant, transitions from one city to another depends on whether or not the city has been visited or the amount of pheromone trail on the edge connecting two cities for the pheromone trail. At the end of a tour, each ant lays pheromones on each edge it has used. The amount of pheromone is proportional to the performance of the ant. Pheromone's intensity on each edge decays over time. Each time an ant moves from one city to another, their pheromone concentration on the edge is reduced. This makes visited edges less attractive and encourages exploration. Only the ant with the best tour lays pheromones. It also encourages ants to search paths near the best bounce so far. And these are updated rules of the ant colony system.
So a way to translate this to computer speak would be to say that each time an ant does a trip around the graph, that is one iteration where we take random numbers to decide which edges to go through and which nodes to visit on our way back to the first node. Paths that end abruptly without reaching the end node drop. Now, each time that an ant visits nodes, all of the paths it does not take lose a little bit of their pheromone. However, the nodes that it does visit, or the paths that it visits through, do gain a little bit of weight. As this algorithm runs many, many times, there will be many times that it finds, or that it adds weight to the edges. It will add more weight to edges that have a small distance. What this will do is over time, very slowly, it will find the best route until eventually, at the very end of the program, if it runs until completion, there will be one path that has 100% weight, and all other paths will have 0 weight. And the one path with 100% weight will be the optimal path for the traveling salesman.
Okay, and this example in our picture A, it shows all the visitations of the ants, and on all of the edges, it shows the pheromone trails that they have left behind. The lighter edges are where the pheromone trail has been reduced based on its concentration. The bolder edges is where it resembles the shortest path, which is the best solution found by the ants. And picture B shows its end result, which is the shortest path. Are there any quantum algorithms? Yes. In the academic journal that we provided called Efficient Quantum Algorithm for Solving Traveling Salesman Problem in IBM Quantum Experience, which is written by these 4 people, they provide and discuss an efficient quantum algorithm for the TSP. The quantum algorithm they mentioned uses the phase estimation technique to solve TSP. It is also cited below in the references. In conclusion, the traveling salesman problem can be solved using different meta-heuristics and approximation algorithms. The ant colony system is one of the many meta-heuristics that we have chosen, which is discussed to solve the TSP with this observation of an ant colony's actual trail of pheromones to gather food. Finally, we came across that there is a quantum algorithm to solve TSP more efficiently, which is provided within the paper we cited. These are our references below, which also includes the paper. And thank you for your time.
Thank you so much.